This required uh, bringing in talent, which I could, but to bring in the talent, I needed the money. Okay, and as an assistant professor, given this responsibility, there were those were rough days. Okay, when you knew that you could get very good people, but you had to find the money, and there were not enough banks to be robbed. And this is where Research Corporation was very helpful. And I'll tell you what I did with your money, and hopefully you're proud of it. So, pardon me.
So it's good. We got finally get a report on how to use the money.
Here is the thing: if you don't like the report, the money is all gone. I spent it all. So there are a couple of mysteries which motivated this work. One that is visible to all of us, and that is the puzzle that in the visible universe that we see, there is no 4th of July happening. A 4th of July as in matter and antimatter islands coming together, annihilating each other. You just don't see that stuff happening. It would be spectacular if it did. And it looks like the only thing we can do is set limits on how much antimatter, primordial antimatter there is in the universe, when in reality, Big Bang would predict that there were equal amounts of matter and antimatter when that happened. And so the question is, where has all the primordial antimatter gone? Okay, without essentially a trace. And the way we can tell that there isn't such thing as antimatter, primordial antimatter, there's some amount of antimatter which is made just from E equals mc squared, but we're looking for the primordial antimatter and it doesn't seem to exist. So question is, what was the disease that antimatter had? Andrei Sakharov in 1967, actually a few years after about the phenomenon that I investigated was first seen in a system called kaons. He said there are three things that must happen, three conditions must happen for this asymmetry that we see, much more matter than antimatter, to happen. First of all, proton must decay. Actually, so far, we have seen no evidence that the proton decays. And during expansion of the universe, it should not attain thermal equilibrium, so there should be unequal number of particles and antiparticles. But here is the one that was of interest to me, is that the symmetry between matter and antimatter must be violated. So there must be a way by which you can tell matter from antimatter. Okay, so when you see an alien the next time, before you hugging them and therefore destroying yourself, it's better to check whether they are made up of matter and antimatter. So what experiment would you make them do to see if it was safe to hug them, in some sense? So rather than tell you the physics of all this, which is complicated and takes a long time, I'm just going to tell you that there are discrete symmetries in nature which have been extremely useful in physics to describe subatomic phenomena. There are three of them. One is, I show here two of them. So here is a hand, and here is the reflection, the parity reflection in the mirror. It looks like that. And here is a hand, and here upon charge conjugation, this is matter, this would what, let's say, is the antimatter part of it. Okay, so you see that these are different. But if you look at a hand in the mirror and its antimatter form, then they look very similar. Okay? So this is called CP symmetry between of a system. Unfortunately, if this CP symmetry existed, then this would be like taking two hands, one matter hand and another antimatter hand, and matter and antimatter, and as they came together, they would all, if they were perfectly aligned and matter looked just like antimatter, then this touching would be perfect, and all matter and all antimatter would go, and so you wouldn't be here, okay, and I wouldn't be here to tell you. So there had to be some sort of a misalignment, if you will, between matter and antimatter such that just one element of matter out of tens of billion survived the antimatter. That everything else got destroyed, and just a tiny amount survived, and it is from that tiny amount that you have galaxies and stars and flowers and you and I. So question is, how is CP violated? Okay, how do you tell the difference between matter and antimatter? And uh, it turns out the CP violation was actually seen in a Nobel Prize winning experiment in 1964 in a system called kaons, subatomic particles made up of kaons. But these particles were so light that it was very difficult to understand the system. If you don't understand the system, then you can't understand its properties well enough. And so CP violation remained a puzzle until 1995, 96, when this experiment was being built at Stanford. The experiment that was being built at Stanford was actually motivated by a different reason, and that was this. Everything that you see around the universe, including you, I, the protons and the neutrons and the atoms, they're all just made up of just a set of quarks called up and down whimsically, and electrons and electron neutrinos. This is how you make a hydrogen atom. This is how you make up the entire periodic table. This is all you really need. That plus little photon, little weak interaction, and little gluons to make nuclei. And of course, the Higgs boson, that's another story that I was involved in, which I'm not going to talk about. So this is all that was required. This is the minimalist requirement. But nature was very generous. And what it did was it essentially gave us 3 replicas of the same thing. Okay? Nobody needed this, nobody needed that, but it exists. And the only way that they are different is that they all have different masses. So there is up, there's a heavier version called charm, there's an even heavier version called top quark, which was discovered just about a decade ago. So the question is, why do you need these 3 generations? And why only 3? Because we searched for 4 and we couldn't find it. So in that sense, the question is, if 3 is the answer, then what is the question? Okay? And it turns out that what Sakharov was saying, what you see in terms of absence of antimatter in the universe, and the fact that there are 3 generations are intimately related in the sense, and this is what was a conjecture by these 2 Japanese physicists, theorists, Kobayashi and Masukawa. This is back when they were postdocs in 1972. And they said, to see the matter-antimatter asymmetry, there has to be CP violation in subatomic systems. And they predicted, and at that time, we didn't know that there were 3 generations of identical stuff. And they predicted there must be at least 3 generations of quarks in order to develop a quantum mechanical phase. We won't get into technicalities of that, but 2 is not enough. For a complex phase, you need 3 generations. And lo and behold, since 1972, the 2nd and the 3rd generation showed up. Okay? So if the answer was 3, the 3 was because without it, there would not be a quantum mechanical phase, and therefore there would not be matter-antimatter asymmetry. But this was a conjecture. And to prove that this is indeed the case, we decided to do an experiment, and this is the experiment done at SLAC. And it's done with a much heavier form of kaon called B mesons. This is from the 3rd generation quarks. But the B mesons have an interesting habit. They are particles, they're neutral particles, but like Two-Face character, if you're familiar with Two-Face in Batman comics, they can't quite make up their mind whether they want to be matter or they want to flip themselves by themselves without any external input into antimatter. Okay? Before coming here, I discovered another form of such particle which transforms itself from matter to antimatter at terahertz, okay? Which means very, very frequently, a completely schizophrenic subatomic particle. This one is just mildly schizophrenic, which means that sometimes after it is born, to the time that it dies in 10 to the minus 12 seconds, picoseconds, there is a finite chance that it will transform itself from matter to antimatter. So just think about it. If you have a source which can be matter at some times and antimatter at the other times, and you could just study them in these two forms, this tells you a lot about what is different between matter and antimatter. That's the take-home message of doing this experiment, okay? That you prepare a beam of particles and you watch them die, okay? And as they die, before they die, you figure out whether this was matter dying or antimatter dying, because both matter and antimatter will die in a picosecond or so, okay? Picosecond is a very small time interval, and part of the challenge of doing this experiment was to actually be able to measure things at a picosecond time scale, and do not to one prepared system, but to billions of such two-phase characters, watching them decay, okay? So let me just show you a little bit of an animation of how this was done, what was the idea, and then I'll quickly jump to results because I don't have that much time. So here we prepare matter, antimatter, they hit each other, and they produce these B mesons. There's a beautiful quantum mechanics here. They're in quantum coherence. Then one of them dies, a clock starts, I start measuring it. That tells me that the particle here is matter or antimatter, and then I watch the clock go, and I watch how many of them die as a function of time. So I have matter, a distribution of those. I have antimatter, a distribution of those. And if their time behavior was different, then you have found that there's a difference between matter and antimatter. And so this is the experiment that we did at SLAC. We should move on. This is the Stanford Linear Accelerator Center. This is reused particle accelerator where we took matter and antimatter electrons and positrons, swung them around, and then hit them right here in the middle of a camera, a multi-ton camera, which can take pictures at several gigahertz. And it is these pictures that we looked for to see the distribution of how tagged matter and tagged antimatter forms, how they behave differently as a function of time. This machine, contrary, was novel, first of its kind, and nobody expected it to work quickly. But it turned out that it was a spectacular success, and it achieved within a year or two something that people were expecting would take it 10 years to accumulate large statistics. So we were very lucky. By the time, and thanks to your money, we built up a fairly large group. And after collecting all the data, we sat down in an open area at Stanford here. So this is my graduate student, Shahram Rahatlaw. This is a postdoc, Gerhard Raven. This is Daniele Del Rey. And then these are other people this is a Santa Barbara person, Owen Long, who used to work with me. And so we had the whole analysis completely blind. So we didn't know the final results until we were sure. And then we just basically removed the tape to see what the final picture looked like. Is matter different from antimatter or not? And you can pretty much guess that we were very tense. You see, everybody has forced smile on their faces. They're not smiling, they are worried, okay? And here it is. This is matter in red as a function of time, and this is antimatter. And so the behavior, the way that these are dying, the way they behave in terms of time is very different between matter and antimatter, okay? And this is the first time we showed clearly that in very not so subtle way, matter and antimatter are very different, just as was predicted by Kobayashi and Maskawa. And so this result, this graph essentially was the experimental proof behind a conjecture from 1972 by Kobayashi and Maskawa, for which they got the Nobel Prize in 2008, okay? So we helped them get the Nobel Prize by doing this experiment. That's pretty much the story. We did see difference between matter and antimatter, but for full disclosure, the strength that we saw of weak interaction is in its ability to explain this asymmetry is too small. And so the puzzle of why there is no antimatter that we can see that is still around, and we have no explanation yet. There are many explanations, but nothing that has been experimentally tested that exists. And so the quest goes on, but during this quest, science works in small steps. Here was one major step where you could do an experiment where you could see the difference between properties of matter and antimatter. So that's pretty much the story. This student who was funded by the Cottrell Scholar Funds, Shahram Rahatlaw, he got the American Physical Society's Best PhD Thesis Award at any US, actually North American university or laboratory. So that was a strong honor. He's now a professor at University of Rome, La Sapienza, and was actually my boss at some point. Anyway, so that's the story, and I thank you again for having me be a part of this fairly important experiment. Thank you.